block elements. Look at this here. We'll go with that as the P block elements. We'll discuss that. In this first P block, I'm writing that boron, aluminum, gallium, indium, thallium. Now and carbon, silicon, germanium, tin, lead. And next will be nitrogen, phosphorus, arsenic, antimony, bismuth. Oxygen, sulfur, selenium, tellurium, polonium. And last will be is fluorine, chlorine, bromine, iodine, acetylene. I can go here helium, neon, argon, krypton, xenon, radon. Look at this. This is what I want to say as a P block elements. Now, I want to go in this one by one. I want to discuss with us some important compounds of P block elements. What are all the important properties of P block elements? I want to discuss with you. Look at this. Now we will go as one by one. That gives you makes what we can say some sense, and we'll go with that some, or we can say the basic information. I want to say that. Now I can say polonium acetylene is not required. Why the polonium and acetylene? Why it is not required? Because they are. This is not required. Why? Because they are radioactive nature. Only we are focusing only this. In this neon, argon, krypton, we discuss only the xenon compounds. Some important reactions of xenon compounds we'll discuss in that. And we'll go some majorly about what is general oxidation state. Look at this. We can go, I can say as this is, I can write it as S2P1 configuration. This is what S2P2. I can say this is S2P3. I can say this is S2P4. I can say this is what S2P5, and this will be what S2P6. Now from this, see S2P1, S2P2, S2P3, S2P4 means sulfur also S2P4. Even Sb, that means we can say arsenic, antimony. Antimony also S2P3. Only the valence shell is different. So you should know boron family S2P1. What is general oxidation state? That talks about the valence shell. That means I can say +1 and +3 state. What about in the case of carbon family? We can say as this will be as +2 and +4. So this will be what? +3 and +5 and what? -3 state. This will be what? -2, +4 and +6. In this case what? -1 is general. Fluorine can show only the -1 oxidation state because it's a most electronegativity. The rest of the halogens, chlorine, bromine, iodine, it can show as a +1, +3, +5, +7 oxidation state because of presence of empty d orbital. And especially in these cases, I can say as what is that? Thallium, lead, bismuth. In this case, they can show only the lower oxidation state is most stable due to poor screening of d and f electrons. Now, in this case, I can say the thallium is +1 stable, lead is what we can say +2 is most stable, and bismuth is what we can say +3 is most stable. That means from this, what we can say thallium +3 compounds, lead +2 compounds, and bismuth +5 compounds are going to act as a very good oxidizing agent. And very interesting, we can say that gallium, aluminium, and gallium both are is what amphibolic. Even tin and Bb also, their respective oxides also amphibolic. That means I can say as Al2O3 is amphibolic nature. Then I can write Ga2O3 is amphibolic nature. Then SNO and SNO2 is amphibolic oxide. And I can write PbO and PbO2 also amphibolic. So what is the meaning of amphibolic oxide? They react with acid as well as base. That means the corresponding metal of anything, aluminium, gallium, tin, lead, if you are treated with what we can say sodium hydroxide, they liberate hydrogen gas. They liberate hydrogen gas. Look at this, I can say aluminium, gallium, tin, lead. They are what we can say is the amphibolic oxides. Am I right or not, Cesar? Now, generally what we can say here, the important point, some important thing I want to explain about it. Generally, what type of JEE means question they will ask you in the examination point of view. Let us go with that nitrogen and phosphorus. Let us go with that nitrogen and phosphorus. General property, what type of main they will ask you. Let us take it as I am taking N bond N. I am taking is what? P bond P. Tell me whether the N bond N and P bond P, which is what we can say, which is the strongest bond, I can say that. Whether what I have given here, I have given is N bond N and P bond B, which is the strongest bond. Whereas everybody will think about that N bond. That is incorrect. The strongest one, PP bond is stronger than NN bond. Why is that? What is the reason? The reason is, we can say the nitrogen is what smaller size, which has the non-bonding electron. Because of what the non-bonding electron, what is going to take place? The repulsion takes place. So because of the repulsion, the NN bond is weaker than PP single bond. That's a very, very important point. And next, if we go with that, if I want to go as, let us take it. Look at this. Now, if I am taking as, I'm taking NH3, I'm taking is what PH3, I'm taking ASH3, I can say SBH3, I can say is what BAH3. Let me ask you, among these five, which is a strong reducing agent? Reducing agent means what? Anything which give hydrogen easily. Now take it as, here I can write that N bond H, P bond H, AS bond H, and what? SB bond H, and what is that? PI bond H. Look at this. Among these five, which bond, the BI, the which bond, the H bond easily breakable? That means Ni bond H, because nitrogen small size, bismuth is what? Larger in size. Therefore, Ba bond H easily breakable. Therefore, it can give the hydrogen easily. Therefore, BaH3 is the very good reducing agent. This is the order of reducing property. So, now, take in this case. What is in this case? I want to take it as a what? As a acidic nature. Look at this. Anyway, water is neutral. Now, I want to go with that. Listen, I'm taking. I'm taking as H2S, H2SE, and taking is what? H2T. I'm taking. Can we say that acidic property? The acidic property means what? Anything which gives H plus ion. Now look at the same thing. I can have what we can say. Once it gives H plus ion, here the negative charge, I can say that HSE minus, I can say HTE minus. Please observe that the TE minus is larger in size. The negative charge take part in the negative charge is completely dispersed. More dispersal of charge, more stable. Stable conjugate base corresponding acid is what? Stronger. That means this is order of what we can say acidic nature. This is order of basic nature. This is what? Basic. This is what we can say acidic. That means H2T is strong acid than H2S. Look at this property, general properties. Are you able to follow? And next will be, if I am going in the case of fluorine, generally in the fluorine, what we can say, look at this. I'll go with the fluorine compounds. I want to say as, listen. Now we'll go with the first oxidizing property. What is oxidizing property? Based on the E naught value. We can say that fluorine has the highest E naught value. The oxidizing property is going to be decreases. I can write this as F2. I can write that Cl2. This is what Br2. And this is I2. This is order of what we can say oxidizing nature. That means F2 wants to become what we can say F minus. F2 always become F minus. And what is the reducing property? If we say that, I can write as I minus, Br minus, I can say as Cl minus, and F minus. It's this is oxidizing property. This we can say is what? Reducing property. So because of that reason only, because of this I minus is Br minus, very good reducing agent, you can say that FeI3 does not exist in pure state. Even we can say that BbI4 does not exist as a pure state. Why? Because I minus is very good reducing agent, Bb plus 4 is very good oxidizing agent. Therefore, what is going to happen? You will be getting as a Bb2 plus I2 liberated. This is what is going to happen in this case. Right or not? In the case of FeI3 does not exist. Why? Because Fe3 plus good oxidizing, I minus is very good reducing agent. So that is the reason the I minus and Br minus are very good what? Very good reducing agent. That is the reason. One more thing I want to emphasize here. When look at this, when what we can say, and Cl minus treated with corn sulfuric acid. Look at this. Now I'll tell you that because these are all the important questions. These type of questions only you may expect for JEE mains point of view. Look at this. I can say that when I'm taking Cl minus plus I'm taking is what? Corn H2SO4. In this case, you may liberate is what? HCl gas comes out. Why? Because Cl minus is very poor reducing agent. Therefore, the double displacement reaction takes place. Suppose if it is Br minus plus corn H2SO4, what is going to happen here? The Br minus is very good reducing agent. When Br minus very good reducing agent and H2SO4 is strong oxidizing agent, what is going to happen? You are going to get as a what here? SO2 gas and Br2. Even same reason for I minus plus what? Con H2SO4. You can say here is what as same SO2 plus what I2. That means why I am trying to say that when Cl minus when con H2SO4, Cl minus is poor reducing agent, it cannot reduce it. But I minus Br minus are very good reducing agent. What it is going to happen? They are going to liberate Br2 and what we can say SO2 gas under heating. This is what you have to think about logically. And one more thing, in the case of what we can say the bond dissociation energy of water. What do you think about that bond dissociation energy or bond enthalpy of? Can you give me the order of bond enthalpy of fluorine, chlorine, bromine, iodine? Can we say? See what we'll think generally. What we'll think about fluorine is the most electronegativity. Therefore, the fluorine has the highest bond enthalpy. That is incorrect. The correct order is, look at this. I can write Cl2. I can write that Br2. I can write this what F2. Then I can write this what I2. This is what we can say the correct order of bond enthalpy. Bond enthalpy, or we can call it as a bond dissociation energy, or we can say as bond dissociation energy. So how did you say that this is the bond dissociation energy? On what logic? Look at this. The fluorine is very small size. Because of small size, look at this. I can write it as F bond F, which has the non-bonding electrons. Because of the non-bonding electron, the repulsion is taking place. So because of the repulsion, what is happening? Because of repulsion, the bond easily breakable. That is what the bond dissociation enthalpy. Here we cannot say what about the bond length. If you are asking about the bond length, the order is like this: F2, Cl2, Br2. Extremely sorry, this is the order. This is the bond length order. Because of size, but in this case, please understand bond length is like this. But the bond dissociation enthalpy here, because of the small size, the lone pair, the repulsion takes place because of this bond easily breakable is not related to the bond length because of the non-bonding electron pairs. This is the order of bond dissociation enthalpy. Right or not, sir? Another interesting point, if you go with that compounds, if I want to go with that anything I can take it. First I will go some important reactions, then I will go with the some important compounds of Metabolic elements. Now, look at this. I want to clean this. See, I have taken only the table. I am going one by one. First, we can go with that. What we can say? P4. What will happen? The P4 undergone disproportionation reaction with in presence of what? I can say in presence of sodium hydroxide. Look at this P4 plus what we can say that NaOH. What is going to happen when P4 plus NaOH? What is going to happen? Disproportionation reaction. So what you are going to get it as? You are going to get it as what? H2PO2 minus plus what is that? PH3 gas. That means it's called phosphine gas is liberated. What liberated here? Phosphine gas. P4 undergone disproportionation. Even we can say as, look at this, H3PO2 also undergone. It's a very good reducing agent. In heating, you may get is what? I can write H3PO3 plus what gas liberated? Again, phosphine gas liberated. Even we can say all mixed anhydride. I can take NO2 undergone disproportionation reaction in presence of water. Any oxides, hydrolysis produce corresponding oxacids. NO2 plus 4 state, which gives what? I can write as a HNO3 plus I can write is what? HNO2. So these are all the example of disproportionation reaction. Even I can say that I want to say as halogen, or we can say Cl2, Br2, I2, except F2, the halogens of Cl2, Br2, I2 undergone disproportionation reaction in basic medium. Example I want to say, in the case of what? In the case of Cl2, please note it down. I can write as Cl2, there are two conditions. One will be is what? NaOH is cold. I am taking NaOH is what? Cold condition. And taking is what? Cl2 with NaOH is what? Hot condition. Hot and concentration. Look at this. Now in Cl2 with the presence of NaOH is hot condition, you are going to get as NaCl plus you are going to get is what? NaClO3. Here is what? NaOCl plus what is that? NaCl. Please observe that you are getting two different oxo acids. When you are going to use the hot NaOH, you are going to get NaClO3. If it is cold and dilute NaOH, you are going to get sodium hypochlorite. This is sodium chloride. Oxo acids of halogen. Look at this. But this is what +1 state. This is -1 state. This is -1. This is what +5 state. This is what 0 oxidation state. What is disproportionation reaction? The same element is undergone oxidation as well as reduction. That is called disproportionation reaction. That means all halogen undergone disproportionation reaction except F2. F2 cannot undergo or we can say disproportionation because F2 react with water because it's a very good oxidizing agent. It produces only oxygen gas via HOF. Able to follow. So this is what, see, chain taking only what we can say periodic table. We are explaining that. And next interesting point, sir, what about the reaction? That means how that N2 gas liberated. They may ask you the examination point of view, one by one. Look at this, sir, how that N2 gas, I'll go N2 gas, ammonia gas, how it is liberated. We'll go because this is enough. N2 gas, O2 gas, then ammonia gas, Cl2 gas, how it is going to comes out. We'll take simple example. Now I am going with what are all the conditions to liberate N2 gas. Very simple. Take it as I am taking NH4NO2, ammonium salt. When ammonium salt, anion, what is this anion? If anion is very good oxidizing agent, you may liberate here is what? N2 gas on heating. Now look at this. I can take it as ammonium bichromate, NH4 twice, Cr2O7. This is the anion part. Anion is what? Very good oxidizing agent. And I am going to heating what I am going to get N2 gas. Take the example. Look at this. Now I am taking NH4Cl. NH4Cl heating. Definitely here Cl minus is not good oxidizing. It's a poor reducing agent. Cl2 only oxidizing agent. Therefore, the Cl minus, and I'm going to heat this. What I'm going to get as ammonia gas and HCl comes out. That's all. That is what. If the anion is very good, if anion is strong oxidizing agent, what level N2? The anion is poor reducing agent. Anion is poor reducing agent. You may not get what we can say. You may get as only decomposition reaction. Ammonia gas liberated. So now one more example. The pure nitrogen you may get it as what we can say azide NaN3 on heating, which gives what we can say that N2 gas. That's all. Got it? N2 gas. Even if you get ammonium, what is that? As NH3 twice CO3, ammonium carbonate on heating, what are you going to get? Ammonia gas. That's all. Look at this. This is what the properties of the P block element. See, I have taken the periodic table. From this we are discussing. See, anion is more important. Even the interesting is what? When I am taking as NH4NO3, here, though it is an oxidizing agent, what I am going to get as a N2O gas comes out. Look at this. It's a neutral oxide. N2O neutral oxide. What is that? N2 is what? Bond order is 3. It's a diamagnetic molecule. N2O, it's a laughing gas. We can say it's a nitrous oxide. Are able to follow what this is what in the examination point of view they will ask you. That means how do you prepare N2O? We can take it as a NH4NO3 on heating, produce N2O. It's a nitrous oxide. It's a laughing gas. It's a diamagnetic gas. Hybridization is we can go with the Sp2 hybridization because central atom of nitrogen. Are able to follow what I am trying to say, children? So this is what the inorganic chemistry. See, that very taken inorganic. Logically, we are going approaching the question. However, that's all. Now come to the point. Next will be, look at this. Now we are going with that. Now I want to clean this. Just I am cleaning. I need the, or we can say the space to explain to you. Now nitrogen. Generally nitrogen they go with the what we can say oxides of nitrogen. What oxides of nitrogen? If I am going with that one by one, one will be is what? NO. I'll go with that N2O. I can go with that N2O3. I can go with that N2O4. I can go with that N2O5. That's all. This is oxides of nitrogen. These two are what we can say that neutral. Neutral. These two are is what? Neutral. Remaining three are what? Acidic oxide. Higher oxidation state of nitrogen is a stronger acid. That means in among these three, strongest acidic oxide is what? N2O5. Very simple. When this is react with water, you'll be getting is what? HNO2. When this is react with water, what are you going to get as HNO2 plus HNO3? When this is react with water, this is HNO3. Sir, how to remember this, sir? Very tough to see. Any non-metal oxides, hydrolysis gives corresponding what we can say oxo acids, any non-metal oxides, any non-metal oxides. For example, N2O3 is a non-metal oxide. Whatever the oxidation state, you may get the corresponding oxo acid. But how to find out it, sir? How to find out it? Listen carefully. Now, I will base these two are what we can say as a neutral oxide. That means how to know HNO based on the structure. Look at this. I'll tell you the structure. Look at this. The structure wise, if I want to go, I can go. There are many structures. First, I will go with that. This I am drawing that N, bond N. Look at this. Double bond O, bond O. That's all. I got it. Look at this. Oh, this is the structure of N2O3. Now hydrolysis means what? Bond is going to break here. I can make it here is what? H. Here is what? OH. HNO2. HNO2. I got it. Oh, that's all. Oh, the structure of what we can say as a N2O3. Bonds are going to break here. OH and H. I got it. HNO2. Oh, now come to the point about in the case of N2O4. Look at this. What N2O4? N bond N double bond group. This is bond group. Double bond group. This is bond group. That's all. That's all. Now hydrolysis. Look at this. Here H. Here is what OH. H OH. That means HNO2. HNO3. I got it. Therefore, this reaction is called disproportionation reaction. Why? This is plus 4 state. Plus 4 becomes what? Plus 3 state. This is what is a plus 5 state. This is example of disproportionation reaction. That's all. Now, based on the structure, first I break the bond of these two H and OH. I got this. Then N2O5. I'm getting is what? HNO3. N2O5. Look at this. Now what is the N2O5? N. That's all. Oh, hydrolysis, you do that. H, OH, HNO3, HNO3, I got it, that's all. That means how to find out it? The what we can say the oxidation state of this group plus 3 and plus 5. If the oxides of nitrogen family plus 3 and plus 5 on hydrolysis produce corresponding oxo acids with the same oxidation state. If they have the between oxidation state of plus what we can say plus 4 means they may give the 2 oxo acids. So such oxides are called mixed anhydride. That means I can say that N2O4 is called mixed anhydride. Why N2O4 is called mixed anhydride? Because it produces 2 oxo acids on what we can say hydrolysis. So we are getting HNO2 and HNO3. That's all. Now come to the point about even. We'll go with that lot of information about. Listen. Now we got the idea. Now how to prepare. Look at this. NO gas. Look at this. NO gas. N2O gas. So how to prepare this? This can be prepared by using what we can say dilute HNO3. Look at this. When I'm taking, look at this copper plus dilute HNO3. How to remember this? Copper means what? How to remember this reaction? Please keep it in your mind. Whenever the low reactive metal, such as copper, such as silver, when the low reactive metal react with dilute HNO3, always produce NO3 twice plus what gas liberated? NO gas liberated. When the low reactive metal means what? Silver, we can say as a copper, mercury. The low reactive metal with dilute HNO3 liberate NO gas. Then how to get the N2O gas? Very simple. Take it zinc plus again what? Dilute HNO3. What is zinc is belongs to? It's a moderate reactive metal. When the moderate reactive metal dilute HNO3, what you are going to get? Zinc nitrate plus we can say as N2O gas liberated. Then how to prepare N2O3? Very simple. Take it NO plus what we can say NO2 minus 30 degrees Celsius. You may get as a N2O3 as a blue solid. Blue solution, we can say that. Minus 30 degrees Celsius. It's a blue color one, N2O3. It's an example of non-proportionation reaction. How to prepare, what we can say, NO2, very simple. Take it as BbNO3 twice. Any metal nitrate except alkali metal nitrates, in that lithium nitrate included, because sodium nitrate, potassium nitrate, rubidium nitrate, cesium nitrate, they never liberate what we can say NO2 gas. Rest of the metal nitrate liberate NO2 gas on heating. And I'm going to heat this. I'm going to get what? BbO plus what? O2 plus NO2 gas liberated. What is that? NO2 is nothing but it's a brown gas. It's a brown gas means it's a paramagnetic substance. It's a monomer. Monomer is what? NO2 is monomer. Dimer we can take it is what? N2O4. Dimer is what? Diamagnetic. NO2 is what? Monomer. It's a paramagnetic gas. This is N2O4 is a solid at lower temperature. Then how to prepare what we can say as N2O5? Very simple. Take in HNO3. Look at this. I'm taking as HNO3. I'm taking. Plus we are using is what? P2O5. What is P2O5? Is called dehydrating agent. So obviously what you're going to get as N2O5 plus we are going to get HPO4. HPO3. That's all. That's all. And the very interesting point, please keep it in your mind, whenever, now I want to say that whenever the con HNO3 acts as the oxidizing agent, whenever con HNO3 acts as the oxidizing agent, always liberate NO2 gas. When I'm taking Sp4 plus what? Con HNO3, what are you going to get? In the P4, undergone higher oxidation state of H3PO4. This gives NO2 gas. Take it as a S8 rhombic sulfur with what? Con HNO3. Always goes what? H2SO4. Higher oxidation state. And plus NO2 gas liberated. So when you are studying like this, don't study P4 and S8. Study as a non-metal. When non-metal react with con HNO3, liberate always NO2 gas. This is what you want to what? Understand. Now in the case of I2 plus con HNO3, what you are going to get? HiO3 plus NO2. This is what the idea of the inorganic chemistry. This is what the idea of the inorganic chemistry you need to understand. Now come to the point. The important reaction still I want to give it to you. Look at this. Now this is over. Now we are going with what? Oxoacids of phosphorus. Structures. Oxoacids. Look at this. Oxoacids of phosphorus. I'm going first will be hypophosphorus acid. I can write as this is hypo. Why hypo? Because phosphorus is +1 state. That's the reason S acid suffix and prefix is what? Hypo we have taken. Now let us go with the phosphorus acid. And phosphorus acid, I can take P double bond OH, H. This we can call it as a what is a phosphorus acid because phosphorus is +3 state. It's a dibasic acid. This is monobasic acid. I can say why I have the only one H here. What we can say 2 hydrogen dibasic acid. Now what is phosphoric acid? Look at this. This is phosphoric acid. So now I can say in that hypophosphorus this is +1 state. This is what? +3 state. And phosphorus this is what? +5 state of phosphorus. Now these two are very good reducing agent. Why? I can have here pH 1, 2 pH 1. Anything have the pH bonds are there, they are very good what? Reducing agent. Now we can say here pH 1, here 1 pH 1, here no pH bonds. Therefore this is tribasic non-reducing, dibasic mild reducing. It's a monobasic strong reducing agent. That's all. This is what the logic of inorganic chemistry. Now I want to go with that. as pyrophosphorus. Pyro means what? Pyro means two, di. Pyrophosphorus acid. How I am going to pyrophosphorus? They are asking structure. Pyrophosphorus. Pyro means what? As here, two molecule, and then simple idea. Now take this, I am writing that P double bond O, I am taking as OH, H plus P double bond O, OH, H, OH. Just remove water molecule, just join it. Now observe this, pyrophosphorus and hypophosphorus both can have what you can say. Look at this, how many pH bonds are there? 2 pH bonds. This is what examination they will ask you. Hypophosphorus acid, this is pyrophosphorus acid. And I can say pyrophosphorus and what we can say phosphorus acid, both are is what dibasic acid. Yes, statement is right. Hypophosphorus and pyrophosphorus both have the 2 pH bond. Yes, statement is right. Able to follow? Now what about in the case of pyrophosphoric acid? Pyrophosphoric means what? Look at this. What is pyro? Pyro means what? Di. That means when I'm going with that as P double bond O, OH, here is OH and here is what? OH plus P double bond O, OH, pyrophosphoric acid, remove a water molecule, which we are going to get as P double bond O, P double bond O. I can say this is OH, this is OH, this is OH, and this is not OH. That's all. This is called pyrophosphoric acid. I can write. When two molecules gives what we can say pyrophosphoric acid. So what is hypophosphoric? Hypophosphoric. Look at this. Look at this is pyrophosphoric. Look at this. What is hypophosphoric? Hypophosphoric means phosphorus acid and phosphoric acid between. Look at this. Now, P double bond O, OH, H, P double bond O, OH, remove the water molecule, hypophosphoric. Now what I am going to get it, this will be as P bond P, double bond O, OH. This is called what is hypophosphoric. That means it has only PP bond. So each phosphorus has what we can say. We can say this will have what we can say +4 state and what we can say +3 state. We can say each phosphorus. This will be one will be +4 and one will be what we can say as a +5 state. When hydrolysis, you are going to get like this. Able to follow what I am trying to say that. That means you may say that average oxidation state of the phosphorus is what here +4. Now, next I want to go with that. So this is the oxo acid. Now next, what is cyclic metaphosphoric acid? Look at this. Very important. Cyclic metaphosphoric acid. So how to do cyclic metaphosphoric acid? Look at this. That's all. Oh. Oh. It's called cyclic metaphosphoric acid. Look at this. This is phosphorus. This is what? POP. It has 3 POP bonds. This is what's what? 1, 2, 3. It has more ionizable hydrogen, therefore the tribasic acid. This is what the examination point of view they will expect it. This is cyclic metaphosphoric acid over. And now, in the case of how we are going to get such acids, very simple. Take oxides. When I am going with the oxides, listen. Now I am going with that. Understand? P4O6. We'll go with that P4O8. I'll go with this one P4O10. When you go complete hydrolysis, H2O, what are you going to get as H3PO3 because this is +3 state. plus 3 state gives the corresponding oxide acids H3PO3. Hydrolysis, because this is in between oxygen, the complete hydrolysis, you may get as what? H3PO3 plus you will get H3PO4. And this will be complete hydrolysis, you may get is what? H3PO4. That's all. Now, how to draw the structure of P4O6, P4O8 and P4 water? Look at this. Take it as you want. See how I draw this. Look at that. This is called P4. Now, what do you do? In between PP bond, introduce oxygen. Look at this. O. This is called P4O6. Now P4O8. That's all. P4O10. That's all. This is what you want to know. Right or not? This is the logic of what we can say oxides of phosphorus and the oxo acids of phosphorus is over. Either H3PO2 very good reducing agent. Point is done. Now come to the point next. We'll go with that next week. In the case of what we can say, how to prepare oxygen generally. Very simple. Oxygen, how they prepare? Take when I'm taking Ag2O. Look at this. So what is Ag2O? Lower reactive metal oxides on heating. Liberate O2 gas plus Ag. Low reactive metal oxides on heating produce oxygen gas. Here we know that take it KClO3 in presence of what we can say that MnO2 as a catalyst, what gas liberated? O2 gas liberated. Plus what we can say KCl. You got the idea? O2 liberated. Even hydrogen peroxide is undergone disproportionation reaction. Look at this. I'm going to get is what H2O plus half O2. So preparation of what we can say that oxygen gas over. Yeah. That's all. This is how the gas comes. So then how to prepare Cl2, Vr2, I2 gas. That's very interesting. Look at this. And I'm going, look at this. Now in the case of, I'll take simple example. I'm taking MnO2 plus HCl. Mild heating, liberate Cl2. Once the color of Cl2, we can say greenish yellow, is become Mn2 plus redox reaction. Now come to the point MnO2 plus what? I'm taking Br minus in presence of acidic medium. Br2 it's a brown plus Mn2 plus. Now go with the MnO2 oxidizing in presence of I minus, H plus, I2 plus Mn2 plus. That's all. Look at this. How Cl2 greenish yellow. We can say Br2 is what? Brown. I2 same oxidizing agent. Only thing HCl, Br minus, I minus in medium of acidic medium because Br minus, I minus is very good reducing agent. But here heating is must over. So we know that Cl, even we can prepare as, look at that. IO3 minus plus I minus, you will get I2. Even we can take it as a what? BrO3 minus plus what? Br minus. And take it Br2. That's the reason they will use, especially for phenol in aqueous solution. They will not use Br2 water. They may take KBrO3 plus KBr. I discussed it in the organic chemistry. They undergone con-proportionation reaction because of Br2 tribromophenol. You are going to get it. That's all. And one more thing, chlorine water. They may say the chlorine water loses its yellow color on standing. Why? Because it slowly undergone disproportionation reaction. That means we know that chlorine water means what? I can take it Cl2 plus water. It loses yellow color because formation of what we can say HOCl plus HCl. Chlorine water that loses its yellow color because of what? What is the reason behind this? Because it's undergone disproportionation reaction, formation of HOCl and HCl. Now, we got the idea about that. Now we'll go with the discuss about some compounds of what we can say P block elements. Compound means what? First we'll go with that. Many of them was B2H6. What is B2H6? We can call this here 3 center 2 electron bond is present. I can say I'll go with one by one. First will be is what? B2H6. Next will be I'm going with AlH3. Then AlCl3. Now the structure of generally how to prepare B2H6 means sodium borohydride with Sp2. We will get the B2H6. In this B2H6, what is a? It's a monomer. It's a BH3. Dimer is what? B2H6 is still electrophile, but Sp2 hybridization which has banana bond. So how you are going to explain with this has the banana bond? Look at that. Now I'm going with the boron. I'm going with here also is what? Boron. Observe carefully. Now boron valence electron is what? I'm going with is what? S2P1. Here also is what? S2P1. I'm writing here is what? Just for understanding hydrogen. Listen carefully. Now obviously boron maximum covalence is what? 4. That means it can use S2P, S orbital and 3p orbital. It is going to use for the hybridization. Look at this. Now 1 electron is given to for this. Here, this boron same way. Like this we got it. So now out of 4 orbital, 2 orbital for the terminal. Now I can have here what? Hydrogen. Here also is what? Hydrogen. Now obviously 1 I can use it for this. That means I used 1 electron. Here also what is it? 1 electron. Here also boron is what? Look at this. This boron gives 1 electron. Hydrogen gas gives 1 electron. Now look at this. Out of 4, now what we can say? 1 orbital. Each boron is there. Look at this. This is overlap like this. Overlap like this. That's all. This is called, look at this, BHB. 1, 2, 3 centers are there. How much electron in this one? We have only 2 electrons are there. Now I can say B2H6, it's electrophile, which has what we can say 1, 2, 3 center. What electron? 2 electrons are there. That means this has 3C, 2 electron bonds. How much is there? 2 are there. So BHB, that means we can say 1, 2, 3, 4, 5, 6 atoms are in the one plane. 1 hydrogen above the plane, another hydrogen is what? Below the plane. This bond is called what? Banana bond. What is called banana bond we can say. It's called the 3 center 2 electron bond. Look at this how boron. As S2P1 is the valence electron, boron is what? S2P1 is the valence electron. Yes, we got the idea. Now the 3 will be used. 1 orbital is there. That orbital is going to overlap. That means 1, 2, 3, 4 orbitals are used. What is hybridization? Here will be Sp3. That's all. This is what the inorganic chemistry. We come to know that B2H6. Now B2H6 on hydrolysis, what is going to happen? Hydrolysis. It produces what? H3BO3 plus H2 gas produced. That's all. B2H6 gas, and when they are taking as that's called borosine, they will see inorganic benzene. When that, if I am going to take it as a B2H6 with ammonia, the ratio of 1:2 on heating, which produce B3, N3, H6 plus what is that? H2 gas liberated. How's that? This is called borous inorganic benzene. Look at that. This is called inorganic benzene, borosine. Yeah. Now come to the point of AlH3. So I can say this is dimeric state. You can say as here 3 center 2 electron bond. Now come to the point of AlH3. Look at this. Now I want to clean this. One minute. I want to clean this. Now AlH3. Same logic. This also has 3 center 2 electron bonds. How? Take it as aluminum. What is the valence electron? We can say as S2P1. Now, same logic. Hydrogen used. Hydrogen gives 1 electron. Hydrogen gives 1 electron. Aluminum gives 1 electron. Same here also aluminum is there. Hydrogen, hydrogen. Now 4 hydrogens are there. Remaining 2. Look at this. Above the plane and below the plane. I can say this is an electron is used here. Here also an electron. Same thing. I can say here also what electron used. Now we can say aluminum has one orbital empty p orbital is that's going to overlap here. That's all. Now I can say this bond is called what? Banana bond. Now the dimeric structure, what do we can say? It has 1, 2, 3, 3 center 2 electron bonds. 1, 2, 3, 1, 2, 3. I can say that 3 center 2 electron bond is called the banana bond. We can say that. Are you able to follow? This is the logic of what we can say that in organic chemistry. But what about AlCl3? But AlCl3, it undergone dimerization, but it does not have banana bond. Why? Because when I am going with that, Al, Cl, I can take Cl, I can take it as a Cl. Even look at this Al. You know that chlorine it has the non-bonding electron. That's all. So when it is going for AlCl3 undergone dimeric structure, but it is not electrophile. It is not having 3 center 2 electron bonds. That's all. Now the next will be, this is what, and one more thing. What about in the case of BF3, BCl3 and BBr3? They may ask you the question, which is the strong, the Lewis acid. Generally they will ask you, what is that? BF3. Look at this. So BF3 is there. And BCl3. And I'm going with what? BBr3. So can you say among these three, which is the strong, the Lewis acid? How we are going to, what we'll think about that? BF3 is there. Fluorine is the most electronegativity. Therefore, the BF3 strong Lewis acid. That's what we will think. That is incorrect. The correct order of the Lewis acid order is, we can say, this is the correct order. Why? The reason is what? Very important. Look at this. In the case of boron, there is what? Fluorine. Now, which has, you know that this is Sp2 hybridization. All Sp2. All Sp2 hybridization. Look at this. Now I can have here is what? The lone pair of electron. Now, what is going to happen? Here I am taking BCl. Look at this. Empty orbital. Cl. Lone pair of electron is here. Now, look at this. Like this way. Observe that. In this, how we can say, I told you, order is BBr3 is what? Strong Lewis acid. How I am going to say? Look at that. Now, this I can say as a 2p. This also is for 2p. Therefore, 2p 2p overlap. Here is what? 2p. This is what we can say as a 3p. Here is what as 2p. Here is what as a 4p. Now, what we can say, which overlap is most effective? 2p 2p. Fluorine of non-bonding electron can form a 2p 2p pi bond, which is more effective. Therefore, this boron becomes somewhat less electron deficient. This boron becomes more electron deficient. So, electron deficient species are called Lewis acid. Therefore, the BBr3 strong Lewis acid among these three. That's all. Over. That's a logical. It's not organic chemistry. Now, next one. What about the oxo acids of what we can say? halogens. Very important. Oxo acids of halogen. In the case of what we can say as the oxo acids of halogen, please understand. We'll go with that as one by one. One will be HOCl, HClO2, HClO3, and HClO4. Let me ask you, among these four, which is strong acid? We can say the higher oxidation state strong acid. We'll go with the structure wise also. Look at this O. This is what Cl. This is what H. This is what lone pair of electron. Now go for HClO2. Cl double bond O. I can go with that as OH. Lone pair of electron. Now in the case of HClO3, Cl double bond O, I can write as here OH on lone pair of electron. In the case of HClO4, Cl double bond O, OH, HClO4. Look at this. What I am trying to say that chlorine is the +7 state. One gives H plus N, more number of delocalization, stable conjugate base corresponding acid is what stronger. Therefore, the order of acidic nature is what? Order. Then what about the strong base? This is the order of basic nature. As I can say, weak acid corresponding conjugate base is what? Strong. Therefore, the strong acid corresponding conjugate base weak. And look at this, all the central atom of oxo acid has Sp2 hybridization. Oxygen, Sp3. Chlorine, we can say as Sp3. This also is what? Sp3. Even this also is what? Sp3. That's all. All are Sp3 hybridization central atom. Alright, look at this non-bonding electron pair here. The central atom has 2. This will be 1 and this will be 0. This is what you have to observe that. So this is about the oxo acids of halogen. So that is what oxo acids of halogen. And next will be the case of what I am going with that as xenon compounds. Look at this. In the case of xenon, what they will do, especially xenon compounds, if I am going with as XeF2 and XeF4, and is what? XeF6, very important, plus hydrolysis H2O, hydrolysis H2O, plus is what? H2O. Please observe, in this case, in this hydrolysis, what I am going to get as xenon plus what is that? O2 gas plus H. So XeF2 undergone hydrolysis very fast. You may get the two hydrogen gases. You have two gases you are getting. One is xenon gas, another one is what? O2 gas. And look at this. In the case this XeF4 undergone is what? Disproportionation reaction. How? Look at this. You get xenon plus XeO3 plus what? O2 gas plus HF. Look at this. This is +4. +4 becomes 0. +4 becomes +6. The Nodal redox reaction. That means xenon compounds, they undergone vigorous, especially fluorine compounds, xenon fluoro compounds undergone vigorous hydrolysis. Now come to the point of XeF6. They react with water, but not what we can say as redox reaction. That means you are going to get it as XeO3 plus what is that? HF. But here you may get the intermediate compound. Or you may get one will be XeO2F2 and you may get it as XeOF4. You may get as these two are as here partial hydrolysis. When partial hydrolysis, first you will get XeOF4, you may get it. Another time XeO2F2 you may get it. Further you may get what? XeO3. That means complete hydrolysis you may get XeO3. In XeO3, look at this. This is what structure? Xe. So now we can say there are 3 sigma bonds and what is it? 3 pi bonds. The pi bonds that belongs to is what? It's Sp3 because we can say as a 3 plus 1. 3 plus 1 means what? 4. 4 means what? Sp3 hybridization. Therefore, all what we can say p pi d pi pi bonds. So this is what the inorganic chemistry and very important thing aqua regia. So what is aqua regia? That means when you are going with that aqua regia, it's nothing but it is 3:1 ratio of con HCl and con HNO3 volume per volume. And I am taking as HNO3 plus HCl. Both will be is what concentrated. This also is what concentrated. This is 1:3 ratio. Always produce NO gas. When these two are going to mix, it means what gas liberated? NO gas liberated. Don't forget about it. That means when aqua regia is used for what? Dissolves. What we can say is gold and platinum. And what is going to happen? Look at this. When I'm taking gold, Au plus I take aqua regia. What I am going to get as complex formation AuCl4 minus plus what comes NO gas liberated. AuCl4 minus plus NO gas. What is AuCl4 minus? If I want to say that, as I can say as this is what complex formation. When complex formation was 0, this becomes what +3 state. Now in the case of platinum, look at this Pt plus aqua regia. Look at this Pt Cl6 2 minus plus what gas? NO gas liberated. Remember, look at this aqua regia always liberate NO gas. So look at this. The gold become +3 state and platinum becomes what as +4 state. So this is what the real, what we can say, the inorganic chemistry comes out. So when this is aqua regia, 1:1 ratio of con HCl, and that is called volume per volume. That's what. So this is what you want to study about the inorganic chemistry. I given the entire picture about this. Now, next we will go with the. This is about the inorganic chemistry of the P block elements. Now we'll go with that about the important compounds of coordination chemistry. In coordination chemistry, I want to discuss with that. Listen. We'll go with that coordination chemistry. I'm taking it. Coordination chemistry. In this, what mainly focusing on the coordination chemistry, what are all the important information about the coordination chemistry? There are three important theories. There are three important topics which I want to discuss with you. What is the three important topics? One will be VBT, CFT, isomerism. One is called the CFT, another is called what? VBT, another is called isomerism. And before going to that valence bond theory, crystal field theory, and the isomerism, I should say that how the olden days they used to find out what we can say the complex is formed or not. See, very simple. Complex, if I want to say that when I am dissolved in water, it never gives whatever the ion, it never completely dissociate. Whatever the inner sphere, it never dissociate, never ionizes completely. But double salt, it gives constituents of ions, but it never gives constituents of ions. Which one? As a complex. How they are going to find out in the olden days? See, there is a Werner. He took it as a, there are three complexes he has taken. According to, by doing only what the chemical methods, or we can say as a, whenever the complex formation takes place, the freezing point of solid decrease, or we can say conductance. Based on that, they find out. Look at this. Now, he has taken the COCl3.6NH3. He has taken COCl3.5NH3 and COCl3.4NH3. He has taken, and what he did, he has added AgNO3. When I am adding AgNO3, has added excess of Ag in O3 and excess of Ag in O3. From this, he could able to find out. Here, he find out that 3 mole of AgCl precipitated. Here is what 2 mole of AgCl precipitated. And here is what 1 mole of AgCl precipitated. That's what he find out it. Then, using this amount of AgCl precipitate, he could able to predict what would be the formula of the complex. How? Then from this, he can able to say that CO 6 times Cl3. Here, you can say that CO NH3 5 times Cl2. This is what CO NH3 4 times Cl2 Cl, which clearly says that what? What clearly says that only 3 Cl minus n outer sphere. Here 2 Cl minus n outer sphere. Here the 1 Cl minus. That means here gives 3 Cl minus n, 3 mole of AgCl. 2 Cl minus n in solution, 2 AgCl. 1 Cl minus n in solution. So the remaining part, whatever the inner sphere, never ionizable. That is called secondary valency. Secondary valency never ionizable. Primary valency, it is ionizable, which is satisfied with the, what we can say, that oxidation state of the complex. Fine. And secondary valency is what? Directional, which provide a proper shape. The next theory is called what? Valence bond theory. That's what the valence bond theory gives information about the geometry of the complex. So what gives the information about the valence bond theory? We can say that as per the based on, what do we can say? Coordination number 2, coordination number 3, coordination number 4, coordination number 5, coordination number 6. So what is trying to say that the metal orbital, that means central metal atom has lot of empty orbitals. The empty orbitals can overlap with the ligand orbital, which provide the, what we can say, the hybridization. The hybridization which gives the shape of the or geometry of the molecule. In that there are, for octahedral complex, one is called the inner orbital complex, another one is called outer orbital complex. What is inner orbital complex? Some strong ligands such as CN and CO and ammonia, some strong ligands are present. What takes place? Pairing takes place. If the weak ligands like water and halogens are there, then never, what we can say, pairing does not take place. Then please keep in your mind one thing I want to say. If hybridization of octahedral complex means, we can say only two. One is D2sp3 or sp3d2. These two only possible. If please keep in your mind, for the central atom electronic configuration octahedral complex, if it is D1, D2, D3 configuration, D1, D2, D3 configuration, irrespective of the ligand, always form inner orbital complex. If the central metal atom has the electronic configuration of D8, D9, D10 configuration, irrespective of the ligand, always form outer orbital complex. If the configuration of central metal, electronic configuration of central metal atom, if D4, D5, D6, D7, in these 4 cases only we have to see whether the ligand is strong or weak. If strong ligand, pairing takes place. If weak ligand, pairing did not take place. This is what you have to logically understand about that, the valence bond theory. Ligand orbital and metal ligand gives electron to form, what we can say, the hybridization, which means that ligand orbital and metal orbital take part in the hybridization, which provide the geometry of the complex. That's what the valence bond theory says. That first we will go with that coordination number 6. And one more thing, this theory gives information about a diamagnetic complex or paramagnetic complex. Look at this. I want to go with that. Listen. Now, let us take, I am going one by one. First, in this case, I am going coordination number is 6. Look at this. I am going with, listen carefully. First, I am taking one simple example as FeCN6, or we can say as 4 minus N. First, you should know which is central atom. Ion is central atom. You should know what is electronic configuration of the first series of 3D series of D block elements. We should know. Now, ion I am writing. Ion is what? As ion is D6S2 Now what is ion oxidation state? X, it's a negative ligand, -6 equal to -4, X which is equal to +2. That means ion is what? As a 2 plus state and having is what? D6 configuration. Fine. So I told you D6 configuration means, that means D4, D5, D6, D7. In these four, depends on the nature of ligand, we can say inner orbital or outer orbital complex. Now I have taken this Fe2 plus and D6 configuration. Now draw like this. I drawn that. Now we know that metal atom has lot of empty orbitals. I am writing that. I have drawn this. Oh, now look at the ligand Cn. Cn is what? Strong ligand. He has considered ammonia, Cn, CO, NO2. Am I right? I am writing that Cn minus CO, NO2 minus NH3. N donors are strong ligand. Nitrogen donor and carbon donors are strong ligands. Weak ligands are what? We can say as the oxygen donor. Halogen donors are what? Weak ligand. So weak ligand means I tell you one by one. Now we got this. Now what ligand is present? Cn minus, strong ligand. So electrons are going to take what we can say. Again pairing takes place. Again the Helm's rule maximum free multiplicity. Once the pairing takes place, look at this. 1, 2, 3, 4, 5, 6. Now this 6 orbitals. Why we have the 6 ligands? So these 6 are going to take part in the what we can say hybridization. Now what we can say D2. How many ligands are there? We can say Cn, Cn, Cn. That's all. Now 6. Each Cn can give pair of electron, which forms a what we can say as a D2sp3 hybridization as a what complex? Octahedral complex. Whether diamagnetic or paramagnetic, it's a diamagnetic complex, no unpaired electron. Therefore, this is D2sp3 hybridization. When D2sp3 hybridization, what we can say? It's an inner orbital complex. It's a diamagnetic. This is what you want to find out. Find out oxidation state, then do that. Now I am going some of the complex. This is inner orbital. Suppose I am taking. Look at the same logic. I am going with that. Look at this Fe H2O 6 times. I am taking 2 plus. Now this complex I am taking. Whether it is an inner orbital complex or outer orbital complex, same logic. H2O is what? Neutral ligand. Therefore, what is ion oxidation state? We will go with the ion is what? D6S2. Now here is what? Fe2 plus. We can say is what? D6 configuration. It's what? D6 configuration. Draw the what we can say? Orbital diagram. Just 1, 2, 3, 4, 5, 6 electron is there. Fine. Now what ligand is there? Weak ligand. Therefore pairing did not take place. So now we can say that that's all. Now look at this. What is going to happen? This is only going to take part in the hybridization of water molecule. We can say 6 H2O molecule. So all gives electron to form what we can say 6 ligands and 6 atomic orbitals. Ligand orbitals and atomic orbitals are combined, which produce Sp3D2 hybridization. If D2sp3 inner orbital complex, if Sp3D2 is what? Outer orbital complex. Now I can say this is what as the outer orbital complex. And diode paramagnetic, it's a paramagnetic. I have the 4 unpaired electrons. What is the magnetic moment? Root of n into n plus 2. Over. That means I can write it as root of n into n plus 2. So I can say that root 24. Over. So this is what about the what is the theory is called valence bond. We'll discuss 5 examples. That 5 example which makes clear idea. Look at this. I'm going only the coordination number 6 only. I'm going. Look at that. I'm going taking some example. Look at this. And in this we want to. I'm giving the list of complex one by one. First will be TiH2O 6 times 3 plus. Then Cr NH3 6 times 3 plus. Mn Cn6 4 minus and again. Now next will be CO NH3 6 times 3 plus Ni NH3 6 times 2 plus. They are asking among these 6 complexes identify how many are inner orbital complex, outer orbital complex, and how many are paramagnetic, how many are diamagnetic. That's what the question. So first I am going titanium. We know that this is 1, this is 2, this is 3, this is 4, this is 5. Look at this. Now, first one I am going. First one is what? Titanium, scandium, titanium, D2S2, titanium 3 plus state. 3 plus means what? D1 state. I told you that. If the D1, D2, D3, if the coordination number is 6, so always form inner orbital complex. Now I can write it as 1. I can write this is D2sp3. It's a paramagnetic complex. Now, come to the point of CrNH2. 2 is what? Cr. Cr what? D5S1 configuration. Cr3 plus D3. So we can, I told you, D1, D2, D3, irrespective of the ligands, form what we can say it's a inner orbital complex. Look at this. You can say 1, 2, 3, only these. I can say as D2sp3. This also inner orbital. It's a paramagnetic complex. Fine. Now come to the point. Next will be MnCN6 4 minus. I want to clean this. Look at that. Look at that. Now I am going with as Mn. It's a third one. Manganese is what? D5S2. I can say as Mn2 plus as D5. What ligand? Strong ligand. Pairing takes place. One, 2, 3, 4, 5. Now because of the pairing, 1, 2, 3, 4, 5. Now they have the empty orbitals. This also is what? D2sp3. So 1, 2, 3. First 3 is what? D2sp3. It's inner orbital complex. This is also what? Paramagnetic. One unpaired electron. √3 is the magnetic moment. Now come to the point of 4 CO. CO is what? As D7S2. What is oxidation state? CO3 plus. You can say as D6. What ligand is present? Strong ligand. Strong ligand means what? Pairing takes place. That's all. Look at this. Oh. It's a diamagnetic complex. It's a diamagnetic complex. It's a inner orbital complex. Now the last one, Ni, that means 1, 2, 3, 4. First 4 is what I say, inner orbital complex. I can say this is paramagnetic, paramagnetic, paramagnetic is what, diamagnetic. And last, look at this now. Last one is what I can go with the last one. What Ni, NH6 times nickel. I can write as D8S2, nickel 2 plus. As D8, I told you, if the D6, sorry, D8, D9, D10, the irrespective of the ligands, forms always what we can say, outer orbital complex. That means I can write it as D8. Now I can write it as yes, P3. Now how many unpaired electrons is there? 2. It's all 2 unpaired electrons. And this is 2 unpaired electrons. Obviously what it's a paramagnetic means 1, 2, 3 out of 5, 4 will be is what, paramagnetic complex. So this is about the idea. Now come to the point of coordination number is what? 4. Look at this. Now we'll go with the coordination number 4 in the 2 category. In the coordination number 4, what you can say as coordination number 4. In coordination number 4, we have 2 categories. One is Sp2 tetrahedral. Another one is called Sp2 as a square planar. Square planar. Fine. We'll go to example. I want to take a nickel. I'm taking. Look at this. Ni Cl4 2 minus Ni Cl4 2 minus. In this case, look at this. I'm going nickel. What is nickel? Nickel is D8S2. Nickel 2 plus is what? D8. One, 2, 3, 4, 5, 6, 7, 8. Look at this. Now Cl is what? Strong ligand. The strong ligand, what is going to happen? Look at this, pairing takes place. Now how many ligands are there? 4 ligands. Therefore I can here yes. And here is what? P3 is there. Now this we can call as Sp2. If Sp2 hybridization, in this case NiCl4 2 minus Sp2, it's a diamagnetic complex. Now in this case, if we take a look at the same thing, nickel D8S2, nickel 2 plus again D8, that's all. Now Cl is what? Weak ligand. If the ligand is weak, pairing did not take place. Sp3 tetrahedral. This is what the examination. And one more very interesting case. In the case of, please keep it in your mind, I want to say as clear. Now, I want to clean this. Now, if I want to clean the case of palladium and platinum, please keep it in your mind. Palladium and platinum plus 2 oxidation state. If the coordination number plus 4 always form square planar diamagnetic complex. Diamagnetic complex. So palladium platinum plus 2 oxidation state, coordination number 4 will form always square planar complex. Now the next thing, I'll take one simple example. I'm taking palladium Pd Cl4 2 minus. So now what? Palladium what? Electronic configuration is what? D10 S0. Now palladium 2 plus you have is what? D8. So D8 how you have? That's all. Sp2. So now here ligands will come. This is Cl gives electron. Oh, square planar complex. That's all. Now in the exam, suppose we are taking, look at this, NiCO4. NiCO4. What is hybridization? Here nickel is what? Zero oxidation state. NiCO4 tetrahedral complex. How? Look at this. Now I am taking nickel Ni D8S2. Why nickel is zero oxidation state? Because he was neutral ligand. Now I can write it as D8S2. Now we know that as per the valence bond theory, so what ligand? Strong ligand. Because of strong ligand, electrons, what we can say, pairing takes place. Sp3 diamagnetic. So this is what that real JEE mains type of questions you may expect. You can discuss one question. They may ask you how many of the following complexes are diamagnetic. They will ask you in the exam. How many of the following complexes are diamagnetic complex? Look at this. We'll discuss how many of the following complexes are diamagnetic complexes. We'll discuss one by one. Look at this. We'll go. How many of the following complexes are ions? They are given the 6 complexes. They will ask you to find out how many of the following complexes are diamagnetic complexes. So we have to go as per the valence bond theory. That gives the clear picture. But CFT will give much more clear. But PBT in this molecule you can go a bit easy to understand. Now Ni just now discussed. NiNH3. What is that? What is nickel? Go with that. Ni 2 plus is what? D8. I told you that D8 means how it is going to fill. This is what is going to fill 1, 2, 3, 4. That's all. I told you, irrespective of the ligands. If D8 configuration, irrespective of the ligands, so pairing did not take place. Therefore, first one is what? This is paramagnetic. Second one, CO. What is that CO electronic configuration as? D7S2. Therefore, CO3 plus. So it's a D6. What ligand? F is a weak ligand. Therefore, the pairing did not take place. Therefore, this also is what para. Very interesting here. CO, NH4 and Cl2 are here. What you have to do? Strong ligand is more than what we can say weak ligand. Therefore, pairing takes place. Don't forget about it. Therefore, in this case, CO D7S2. We can say that CO3 plus. We can say as D6. Here, pairing takes place. Pairing means what? It is diamagnetic. Very interesting. C2O4 thrice because of a ring effect, chelating effect. This become diamagnetic complex. We can write as how we can draw is CO3 plus because of chelating. Here is what D6. D6 means what? Pairing takes place. Therefore, this also is what? Diamagnetic complex. Now NaCl4, just now discussed NaCl4 2 minus, that means Ni2 plus has D8, weak ligand, so pairing is not possible, it's a tetrahedral complex, therefore this is paramagnetic. Now look at this AuCl4 minus, very important. What is that gold electronic configuration? Au means D10S1, Au plus 3 means as D8. So now D8, please understand, very interesting here. That's all. So AuCl4 minus is square planar complex diamagnetic. So how many of the complexes are here? The paramagnetic means 1, 2, 3. This is what they may ask you. Arrange in this one, which is the highest magnetic moment. We can say COF6, 4 unpaired electron, here 2 unpaired electrons, here also 2 unpaired electrons. So this is what the examination, the temperament will come. This is what the examination real questions. Now, next one. So what about, they may ask you, can you arrange, they may give like this, can you arrange increasing order of, they may give you following complexes, increasing order of the magnetic moment. What they will do, look at this, I'll take it as, I'm going here, H2O 6 times 3 plus, Fe H2O 6 times 2 plus, Fe H2O 6 times 3 plus, this is P, Q, R. They may ask you arrange increasing order of magnetic moment. Anyway, all three are weak ligands, no problem, pairing is not at all possible. Go the electronic configuration. Vanadium is nothing but as scandium, titanium, vanadium, D3S2. Now what we can say, vanadium 3 plus would be D2 state. D2 means what? It's like this only. That's all. Now iron is what as D6S2. Here is what Fe2 plus. We can say as D6. Now come to the point of last will be ion as D6 Fe3 plus as D1. Please understand. So 5 unpaired electron, 4 unpaired electron, 2 unpaired electron. See the highest magnetic moment, I can say R, then Q, then O is what P. This is the order of what we can say magnetic moment. That's all. This is what that the JEE mains would expect such question for CFT. Sorry, valence bond theory. So next class we'll discuss CFT. Thank you children. Take care. Bye.